We will now take a look at how to graph rational functions in general. We have seen how to sketch the basic graph f of x equals 1 over x, and using graph shifting, we sketch the graph of f of x equals 1 over x minus 1. But how do we sketch the graph of a rational function in general, p of x over d of x? One important thing happening with our graphs of rational functions that hadn't happened for any of our graphs before is that our denominator can't be 0. We saw that if there is a point A where the denominator is 0 and the numerator is not 0, then our function has a vertical asymptote at x equals a. And our function gets really large near a, either going off to positive or negative infinity. Now along with this, we'll use concepts that we use to graph other functions. Like with all of our functions, the x and y-intercepts will play an important role in our graph. And like with polynomials, we'll always want to understand the end behavior of our graph, where the end behavior is what happens to our function f of x as x goes off to infinity to the right-hand side of our graph or negative infinity to the left-hand side of our graph. So to graph a rational function p over d, what we need to find is the y-intercept, the x-intercept, the vertical asymptotes, and the end behavior. Now, to get the y-intercept, we just need to look when x is 0. And we can find the y value simply by evaluating our function at 0. This will give us the coordinates of our y-intercept. For the x-intercept, we need to look when y is 0, or our function is 0. So we need to solve the equation 0 equals p of x over d of x. But if we multiply by d of x on both sides, the left is just d of x times 0, which is 0. But the right, multiplying by d of x, cancels dividing by d of x, and we're just left with p of x. So we can solve this by solving 0 equals our polynomial on top, p of x. But we've already seen how to solve polynomials. And when we solve it, we'll get several values of x, k1, k2, and so on, depending on what the degree of the polynomial is. And for each of these x values, we get an x-intercept, k1, 0, k2, 0, and so on, which we can plot on our graph. Now, for the vertical asymptotes, we look when the denominator d of x is 0. Again, this is a polynomial, and we know how to solve polynomials. Doing this gives our vertical asymptotes x equals v1, x equals v2, and so on, which again we can put on our graph. Now the last thing we need to understand is the end behavior. This is what happens to our graph as x goes to plus or minus infinity, off to the right-hand side or off to the left-hand side. The end behavior is a little bit more theoretical and worth watching a more extensive lecture here. Once we've found the end behavior, the y-intercept, the x-intercepts, and the vertical asymptotes, how do we put this all together in one final graph? Like with polynomials, we can start filling in the gaps in our graph by checking if our function is positive or negative on certain intervals. By where our y-intercept is here, we can see that our function is positive between the vertical asymptote x equals v1 and the x-intercept k2, 0. Now, we know our function can't change when it's positive versus when it's negative between these, because if it did, we would have another x-intercept. So for each interval between an x-intercept or a vertical asymptote, we need to see if our function is positive or negative to fill in the rest of our graph.